So I'm a second-year PhD student at CMU from the Carnegie Mellon Database Group. And today I'm going to be talking about this. Dear UDFs, I broke up with you, but now I'm ready to give you a second chance. Will you take me back? Sincerely, SQL. OK, so SQL and UDFs have had a troubled relationship spanning many, many decades. And today I'm going to be covering this relationship and why it's so troubled, and try to lay rest to this question. Are SQL and UDFs finally ready to be together? OK, so user-defined functions, UDFs for short, are procedural functions written in Python, PL SQL, basically any non-SQL programming language. Let me move the mouse. Oh no. Sorry, we had a very elaborate setup.
We'll fix it.
Sorry about that.
All good? Oh.
OK.
Is that?
A little bit over.
What do you mean, like down?
This way.
This way.
A little bit more. Yeah, that's probably good.
Perfect.
OK. I won't touch it again. All right. So yeah, UDFs, basically procedural functions written in some non-SQL programming language, Python or PL SQL or some other language like that. Today we're going to be talking about PL SQL, but it applies to all these programming languages. So yeah, UDFs are procedural functions that are callable from SQL queries in the same way that you would call a built-in function from your SQL query, like substring or something like that. And when you invoke these UDFs, they're executed natively inside the DBMS. OK, this will make more sense with an example. So suppose we want to show all customers and whether they're a VIP. So whether a customer is a VIP is like specific business logic. So it obviously won't come as a built-in function in SQL. So what we need to do is create our own function, isVIP, that takes in a customer ID and returns a Boolean, whether they're a VIP or not. So the way we do that is we have a create function command with the name of our UDF, isVIP. It takes in a customer key, which is an integer, and it returns a Boolean, whether they're a VIP or not. And we're going to use two variables that we declare at the beginning to determine whether they're a VIP. This one, total, which is the total amount of money that this this customer has spent on orders, and this Boolean VIP, whether they're a VIP or not. So the first statement is going to assign to total the result of this SQL query. So what it's going to do is it's going to sum this column, O total price, which is the amount of money spent on an order, for every single order made by this specific customer. Then it saves that in this variable total. Then we do some simple if-else logic. If the total exceeds 1 million, then they're a VIP. So we said VIP equals true. Else, VIP is false. And then finally, we just return VIP. So all the logic for this VIP stuff is encapsulated inside of this UDF. So there's a number of benefits that you get from using UDFs. You get code reuse. You can just call this function from any SQL query. It's more readable because the UDF logic is separate from the SQL query. And it's modular. If you want to build complex SQL queries, you can just break it down into small UDFs. OK, who cares about PL SQL? This is the language that I chose to talk about today. Why talk about this? Well, it turns out that this is actually the most popular programming language for UDFs, even though you probably have never heard of PL SQL before. So Postgres, SQL Server, and Oracle, 3 of the 5 top most used database systems, all support some dialect of PL SQL as a language to create UDFs. And if you don't believe me, here's this quote from Microsoft from 2017, which says, there are of the order of tens of millions of T-SQL UDFs in use today. So T-SQL is Microsoft's dialect of PL SQL. And they're saying there's tens of millions of UDFs in Microsoft Azure SQL database service with billions of daily invocations. So if you're just talking about Microsoft, you're just talking about their Azure, then you're talking about tens of millions of UDFs and billions of queries per day. So optimizing and making sure these queries with PL SQL UDFs are fast is very important. OK, but there's a troubled relationship, right? What's wrong with UDFs? What's the problem? Well, it all boils down to this right here, RBAR execution. So what does RBAR stand for? Well, RBAR stands for row by agonizing row. And this term will explain why UDFs are so slow and why there's this troubled relationship between SQL and UDFs. OK, so let's go back to our example. we have our UDF, we're calling it for every single row of the customer table, and it's basically just going to treat this like a built-in function, right? Every single customer, you get the customer key, call this isVIP function. And then the way it's going to actually execute this UDF, let's say we have customer key 1, is it's going to jump in to this UDF, and it's going to execute the UDF code statement by statement, line by line. And then it's going to reach this SQL query inside of the UDF, and this SQL query is going to scan the entire orders table, accumulating the total amount of money spent on orders for this specific customer. So if you don't have an index on this column in the orders table, you're going to scan the whole orders table, and that's just for customer 1. So you can imagine that if you're doing this for every single customer, then basically for every single customer, you're calling this UDF. And then every single time you call the UDF, you're scanning the entire orders table. So the complexity of this query is in the number of rows in the customer table multiplied by the number of rows in the orders table. So what that means is if I have a relatively small database where I have 1 million customers and 1 million orders, it's going to take 1 trillion operations in order to execute this query with the UDF. And basically that's not going to finish in any reasonable amount of time. And that's why UDFs are so slow. Because of RBAR, row by agonizing row, we have to call the UDF. And this has created a somewhat bad reputation for UDFs. In fact, there's this very famous blog post from 2006 basically saying that UDFs are evil and that you should never use them. Okay, UDFs are bad, we should never use them, okay, until this paper came out, FROID. So this paper was released in 2017 by Microsoft. And FROID stands for Framework for Optimizing Imperative Programs in a Relational Database, basically making UDFs fast. So why is this paper such a big deal? Well, the reason it's such a big deal is because when you enable FROID, queries with UDFs can run up to 1,000 times faster than when you don't enable FROID. So that's a very big deal. In fact, it's such a big deal that Microsoft actually shipped FROID as a feature in SQL Server 2019. So it's that important that it's actually in the product. It's not just a paper. So what's the key idea behind FROID? How does it work? It sounds magic. Well, the key idea is this. We have our query which calls a UDF, row by agonizing row. And that's actually really familiar to another thing in SQL, subqueries. So if you have a subquery in your query, the way that you would think about it executing is that for every row from the outer query, you're going to reevaluate the inner query. So you see there's some relationship in the way that UDFs get executed and the way that subqueries get executed. But the difference is, even though logically you've written a subquery, there's decades of research on how to optimize subqueries. And database systems, in many cases, can rewrite your subquery to use joins, right? So instead of evaluating the subquery over and over again, it will efficiently evaluate your query. So if we can somehow convert a UDF into an equivalent SQL subquery, then we can get really good performance. And that's exactly the idea behind FROID. Can we convert UDFs to SQL subqueries? And the answer is yes. Okay, so I'm going to explain how all of this works. The technique of FROID is this thing called UDF inlining. And the idea is essentially you translate your UDF, which looks something like this, into your SQL subquery, and then you inline it by swapping out the call to the UDF with the translated SQL expression. And I'll explain how this works for our VIP UDF. So high level, we want to translate all the statements in the UDF into SQL, chain them all together into one subquery, and then swap it in. Okay, so how would you translate this into SQL? Well, the idea is that basically you can create a table using this concept. So instead of doing total equals some query, we get the result of that query, and then we save it as a column called total. And then this is going into a table, T1. So what this is doing basically is it's creating a table, T1, with a single column, which just has total, and one row, which just contains the result of this SQL query. And by doing it, this assignment is equivalent to this SQL table. Okay, so how do you handle things like if-else logic? Well, that can be mapped to case-when statements in SQL. So instead of if total is greater than 1 million, you just create a case-when statement where you save the result of the case-when statement as VIP, again, in a new table, T2. Okay, so we've translated all of the statements inside of the UDF into SQL tables, but we have a problem. the second table, T2, is referring to a column from the previous table because it needs to check the total value to determine whether the customer is a VIP or not. So how do you, okay, so that goes away. So how do you make it so that one table can refer to another table? There we go. So how do you make it so that one table can refer to another table's columns in SQL? Well, there's this special magical keyword called lateral. So lateral in SQL creates a lateral join between tables. And essentially, it allows later tables in the lateral join to reference the previous tables in the lateral join. Sounds esoteric, but it's very useful in this particular circumstance. So conceptually, the way that a lateral join is going to execute is as a bunch of nested loops. So you can think about it as, OK, for every single row of this first table, let's evaluate the result of the second table. And if there were another lateral join, it would be another nested loop. So another nested loop. So basically, if you have a bunch of lateral joins, it's kind of like nested loops in the way that it gets executed. So by doing this, this last table has the VIP column, which is essentially what we want, the result of the UDF. So all we do is we just select that column from that table, and then this whole thing is our SQL subquery, which is equivalent to the original UDF. So the last step is you just inline it. You just swap it. You swap the UDF call with this translated SQL expression, and then now you have a pure SQL expression, no UDFs. And this is the reason why FROID is able to get such huge speedups, because instead of having this UDF, which is an opaque function call that the database system can't reason about, the whole thing is now just in SQL, which the database system knows how to optimize. The problem, of course, is that this subquery is extremely complicated. And pretty much no database systems are able to effectively optimize it because inlining the entire UDF is creating such a complex query. So what's going to happen when you have a really complicated subquery? Well, the database system is not going to get rid of that subquery, and you're essentially going to get something very similar to RBAR, where you're just reevaluating the subquery over and over and over again in pretty much the same way as you were calling the UDF. So inlining is not really effective when you inline the entire UDF and you get these complicated subqueries. And the reason why is because really what we're relying on is the database system's subquery unnesting optimization. So unnesting basically is removing a subquery and replacing it with some sort of join. So take a really simple query like this. For every single order, we want to evaluate some subquery. And what the subquery is doing is it's essentially finding the name of the customer who's made a specific order. So pretty much every single database system is going to rewrite this into a join between the customer table and the orders table. And then you've gone from something that's number of orders times number of customers into number of customers plus number of orders if you're using a hash join or something like that. But again, the problem is that when you have these really complicated queries, you're essentially unable to unnest it with any database system, and then you're left with RBAR execution. OK. But actually, there is a way that you can unnest any subquery using this paper from 2015 called Unnesting Arbitrary Queries. It's out of TU Munich in Germany. And if you implement their really fancy algorithm, any subquery can get eliminated. And even with the most complicated inline UDFs, you can get really good performance. But are there any open source database systems that actually implement this? Well, DuckDB partially implements it, but DuckDB doesn't support lateral joins. So if you inline something and it has a bunch of lateral joins, you're not going to be able to execute it with DuckDB, even though it's implemented this paper from Germany. So I need this for my research. So what I did is I spent a semester with 2 master's students actually implementing it in DuckDB, and we put in a pull request, and it's merged. So it's merged in version 0.9, and if you run DuckDB after this version, it's running this code. And you can scan the QR code if you want to check out the pull request. All right. But if you're not dealing with a system like DuckDB, you're still kind of screwed, right? Because you have these really complicated subqueries. The database system can't optimize it. We're screwed, right? OK, so clearly, inlining is not working. Right? And at the same time, I'm doing long distance with my girlfriend back in Australia. And then, I'm staying up at night, calling her. It's taking up all this time. And then my advisor DMs me on Slack, listen, Sam, if you're serious about databases, you need to break up with your girlfriend. This long distance thing is taking up way too much time, right? So normally I'd question something like this, but he's one of the best database researchers in the world, so he must know what he's talking about. But at the same time, I'm not going to fly all the way back to Australia just to break up with my girlfriend and then fly all the way back. So I just sent her this breakup text, long distance isn't working out so great for us, we should see other people. And that's actually how I came up with the title for my next paper. Dear user-defined functions, inlining isn't working out so great for us. Let's try batching to make our relationship work, sincerely SQL. Batching doesn't really work either, but the point of this paper is just that inlining doesn't really work. And things are pretty dire. Inlining is not working. I'm still single, right? So I really have to make UDFs fast, okay, and quick, okay? So I did just that. And essentially, I came up with this new technique for optimizing UDFs called PRISM, which was recently accepted to VLDB 2025. So the key idea behind PRISM is this. Can we eliminate all of the lateral joins by outlining pieces of the UDF? So essentially, the problem with these existing inlining techniques is it inlines the whole UDF, even though we actually only care about inlining important pieces that actually make queries faster. So can we outline the pieces of the UDF that we don't care about, so we're only left with the pieces that we do care about? And the reason it's called PRISM is because it's just like a prism of light, where you take in a UDF and you break it up into its different pieces, okay? Where this piece you might inline, and this piece you might leave as a UDF. Okay, and PRISM comes from these 5 separate optimizations that we implemented, because it's a compiler that transforms this UDF. And I'm going to be talking about 3 out of 5 of those optimizations. So this is the most important optimization, so definitely pay attention to this one, okay? So region-based UDF outlining, okay, what the hell is that, okay? So essentially the observation is this. Out of all of this code, we only really care about inlining this first select statement. Everything else, this if-else logic, we don't really care about, and it's just going to complicate the inline query. So what if we could hide this code behind a function call? We sort of extract it out. So the reason that we can do this is because this is called a region in compiler terminology. There's only a single way that you can get to this region. You have to execute the previous line of code before it, and then you hit the if. And then there's also only a single way to leave the region with this return statement at the end. So because you have a single entry point and a single exit point, it's called a region. And what that means is that you can extract it into its own function, where you call the function at the beginning, and then it returns back to the original UDF. So essentially, we're inserting here a function, return some function, where the idea is that this function should just do the same exact logic as this region. So to do that, we need to think, what are the inputs to the function and what are the outputs to the function? So the way we think about that is which variables enter the region and which variables leave the region. So the only variable entering the region is this total. So that means we're just going to have a f of total. And the only variable that's leaving the region is VIP. So it's just going to return the value of VIP, and that's going to be the return value of f. And then essentially, as long as this function does the same thing as this block of code, we're going to get the same result. So we create a function, takes in total, returns a Boolean, the VIP, has the VIP variable, does the if-else logic, returns VIP, and then we're back here. So what we've done is, because this function does the same thing as the block of code, we can get rid of the block of code and just leave the function. So what we're left with is just this, or if you clean it up, this. So essentially, total equals the select statement, which computes the amount of money spent on orders, and then we just return this function f. And what we've done is we've created a much simpler UDF, so when it eventually gets put inside the colon query, it's going to be much easier to optimize. So the next optimization is this, instruction elimination. So why do we need another optimization? Well, recall that with inlining, what happens is you translate all of the statements individually, and then you stick lateral joins between them. But we want to get rid of the lateral joins. So the way that we do that is we want to eliminate as many lines of code or statements as we can. So what we do is, instead of assigning into this total variable and then immediately passing the total variable into this function, we can just directly put this select statement inside the function call. And that's exactly what instruction elimination does. So now we're just left with a single return statement. And then the last step is called subquery elision, fancy word, But essentially, the idea is just that instead of inlining, which creates a subquery and wraps all the UDF logic, we can just directly inject the return value of the simplified UDF into the calling query. So before, it was calling this isVIP UDF. And since we've simplified that down, so it just returns f of select, we can just directly inject that, and we're left with this. So what we're left with is a query with 0 lateral joins, because we've hidden all of those pieces that we don't care about through outlining. We're only inlining the piece that we actually care about, which is this select statement. And this is in comparison with inlining the entire thing, which is this hugely complicated query, and then you end up having to run an RBAR because the database system can't optimize it. OK, so experiments. So we implemented our approach in PRISM. So PRISM is our approach. We implemented it in DuckDB and SQL Server. And we ran the Microsoft Proc bench. So this is a benchmark from Microsoft with real-world queries with UDFs. We ran it at a 10 gigabyte scale factor. And this was run on a machine Xeon 20-core Intel CPU, 192 gigs of DDR4 RAM, 960 gig NVMe SSD. And what we did is we did 2 cold runs just to load the pages into the buffer pool. And then we did 5 hot runs and then took an average of the 5 hot runs. And the numbers were very stable. So essentially, for our first experiment, we're just interested in, OK, after doing our approach where we simplify the UDF through PRISM, through outlining, are we actually producing something that's simpler to unnest? So meaning getting rid of the subquery, turning it into a join. So if we look at inlining the entire UDF on SQL Server, what we find is that it can only unnest 4 out of 15 of the queries with UDFs. And the reason why is because it's inlining the whole thing, and it's super complicated. But after our approach, where we're only inlining the pieces that we care about, we can, the database system, SQL Server, can unnest 12 out of 15, so 3 times as many queries with UDFs. And as a result, as we'll see in the next slide, that means that for those 8 queries, you're going to get much, much better performance because you're using joins instead of subqueries. Now for DuckDB, because it can unnest any arbitrary subquery, it actually doesn't matter if you're generating a subquery that's super complicated or quite simple, because it can unnest anything. OK, so in terms of the overall speed up of our approach, PRISM, versus just inlining the entire thing, we just report the average and the max. So the average excludes outliers, because there's some very strange queries, as we'll see. And then the max is just to see like what is the extreme case speed up that we get. So for SQL Server, we get a 298.7x speed up. And again, this makes sense because you're going from essentially this really slow RBAR way of doing things to using joins. And actually, in the best case, it's 3,000x faster. Again, because you just have an extremely slow query running RBAR instead of with joins. Now for DuckDB, you could say, OK, well, if it can unnest anything, why does it matter if you're producing some query that's simpler? Isn't the result going to be pretty much the same? But actually, we find that it's still something like 1.29x faster to run it with PRISM versus just inlining the whole thing. And the reason why is because when you inline the whole thing, DuckDB wastes a bunch of time executing those lateral joins, whereas with our approach, where there's no lateral joins, it doesn't have to execute them, so it's just much faster. There was this really weird query where we're just like 2,000 times faster on DuckDB with PRISM. And the reason for this is, again, when you generate a really complicated query, even though the database system can unnest it, it picked a really bad query plan. So actually, generating a simpler query plan, which is what we do with PRISM, ends up having a big payoff. And this was kind of unexpected. OK, so to answer the question, are SQL and UDFs finally ready to be together? And I say, after this work, yes. SQL and UDFs, they're great. UDFs offer all these benefits. And as long as you use the right techniques, you can make them faster. So this begs the question, if SQL can give UDFs another chance, maybe my ex will also give me another chance. So I messaged her this. I broke up with you, but now I'm ready to give you a second chance. Will you take me back? But unfortunately, my message didn't go through because she actually blocked me on every single social media platform. So anyways, to conclude, UDFs are awesome, but hard to optimize. Inlining is this amazingly great technique, but because it's inlining the whole thing, it generates very complex queries that are just really hard to optimize. to get the best performance, you need inlining and outlining. And I'm still single. Thank you.
When you get a question, repeat it.
Yep. Mm-hmm.
How did you decide that a region was good for outlining?
Yep, that's a great question. Let me see if I can go back. So the question is, how do you decide which regions to outline? Yeah, let's say here. So we have an algorithm that's in the paper, and the idea is essentially that you want to outline every region, or like the biggest possible region that you can that doesn't contain any select statements, right? Yeah, because you really need to inline the select statements. Everything else you don't really care about. Yep.
I mean, I have some questions about the Pavlov, like whiplash sort of situation, the relationship. But I'll ask about the sort of history here. Like, this seems like really fruitful, but then like something was merged in 2019. Like, aren't UDFs like really old? Is like PSQL like really old? Like 2019 seems like quite recent.
Yeah. So the question is essentially, UDFs are really old. Why is it that these UDF optimization techniques are so recent, right? So PL SQL was created, I think, in the 1990s, so quite some time ago. And this FROID paper came out in 2017. So that's, I don't know, maybe 20 years or so before like real optimization techniques have come out. And the answer is that it's just a really hard problem because you need to have this knowledge of database systems and also this knowledge of like compilers and programming languages. And to be honest, this inlining thing is really complicated. If you told me, hey, there's a way of turning any UDF into a SQL subquery, I would say, wow, that's really impressive. I didn't, lateral joins, what? Like, is that even possible? So I think it took a lot of time with people knowing both sides, databases and compilers, to come up with this. Yeah, that's why it took so long. Yep.
So for the FROID paper, were they getting the speedups just with inlining, or were they also doing the unnesting?
Right. Yeah, it's a great question. So the question was, with FROID, they have these really big speedups. Let me go back to it. Yeah, so say here. They have all these really big speedups. Is that just inlining, or is that unnesting? What's going on? So the way it works is that when the user runs a query with a UDF, it translates it into SQL or something like that. And then you're left with the query, which has SQL, and then that subquery inside of it. And then the idea is that because SQL Server is a database system that already has these subquery unnesting optimizations, after inlining is done, it's going to run all those optimizations automatically, like out of the box, and then they're measuring the runtime of that optimized query. Yeah. Yeah.
Are there any major database systems that implement FROID out of the box?
Yeah, so you're saying, so the question was, are there any other database systems besides SQL Server that use something like FROID? Okay, well, this is patented by Microsoft, so that would probably explain why no other database systems implement it.
Have you thought about upstreaming the changes to DuckDB?
Right. Yeah, so this is something I'm thinking about, but it's tricky because actually with DuckDB, the use case is that everything is local, that everything is just running in process. Whereas if you think about UDFs, like a big reason you'd want that is the database system is on a server and you want to push the UDF code or like your logic to the server. So the use case of UDFs locally is less useful, I guess, than on a traditional like cloud database system. Yeah. Yep.
So, I mean, does this mean I can use UDFs now? I guess something I'm curious about as like as a user of SQL is like, how do I know if you know, whatever crappy code I write will get optimized by FROID and PRISM, or if it will go back to RBAR?
Right. Yeah, so the question is really good. It's like, can I use UDFs now that these techniques exist? And how do I know that if the database system is actually using these techniques? Yeah, so really, okay, well, the first way that you would know is you run your query and it's extremely slow. That means it's not using any of these techniques. Yeah, so with SQL Server, it's always using FROID, right? Just out of the box, you don't have to do anything. The hope is that PRISM would also be merged into a system like SQL Server. Maybe eventually, that's the plan. But really, there's no way of knowing unless you inspect the query plan. So if you use SQL, you can use like explain or something like that, and it will show the query plan. And then what you should see in the optimized query plan is that there are no UDF calls, that it's just been, it's just like a subquery or something like that. That would mean that these techniques are actually being used. If the UDF call is still there, then the database system is not doing anything. Yeah. Yeah.
How much of your compiler would you get to reuse if you wanted to do this with Python?
Yeah, so actually my next research project is to do this for Python UDFs, and everyone I've told about it has said good luck. So the answer is not much.
My question was related, which is, is anyone considering turning UDFs into batch-oriented?
Right. Yeah, that's a great question. So I think the idea is so to repeat the question was, okay, if RBAR is so slow, where row by row you're re-invoking the UDF, can you use batching or some sort of, better approach so that you're only re-invoking the UDF code per batch? And actually, that's exactly what we explored in the CIDR paper. Let me get back to it. Sorry, forward, not backward. Yeah, this one with the crazy name. So with this paper, we actually tried that. So we sort of rewrote the queries with UDFs, so they pass in a batch, or like a table really, into the UDF code. And then the UDF code would operate on a batch by batch basis. And that definitely did improve things. And it's probably less complicated than either inlining or outlining, because you don't need any compiler in the mix. But the problem is that you quickly run into problems where to really solve the problem, you need a big enough batch size. And then if the batch size becomes too big, then you're starting to spill the pages in the buffer pool to disk, and then you're screwed. You may as well just do RBAR. Yeah. Yeah.
Is there some data available on what fraction of users are using PL/SQL versus Python and other languages? How popular is Python?
Yeah, that's a really good question. So the question was, is there any way of knowing what languages people are writing their UDFs in, whether they're PL SQL, whether they're Python? So unfortunately, the answer is no. In fact, at least as far as I'm aware, there are no public numbers on how many Python UDFs are in active use. The best that we have is that quote from Microsoft, and that's just for PL SQL. Let me see if I can find it. Yeah, this quote. So I wish I knew the answer. But interestingly, it feels like there's sort of this older generation and newer generation when it comes to UDFs. There's this older generation like Postgres, SQL Server, Oracle that are all handling PL SQL UDFs. And then there's this newer generation, specifically like in the analytics side, like Redshift, Snowflake, Databricks, and they don't even support PL SQL. They just handle Python UDFs. So that's why my next research project is going to be about Python UDFs, because that's really what the modern UDF programming language looks like. Yep. Yep.
Do you know offhand if most of these people supporting, or companies supporting Python UDFs are exposing the ability to do select queries or effectively query large tables as part of their row by row execution?
Right. Yeah, so Python, so the question was, so for these Redshift, Databricks, Snowflake, what have you, do they allow you to have these embedded select statements inside of your Python UDF? So in most cases, I believe the answer is no. So you just have a raw Python function, no embedded select statements. So yeah, it's kind of a different problem in terms of what's hard about optimizing Python UDFs. In this case, you have to handle the embedded select statements, which is tricky. Whereas in the Python case, you have the fact that it's dynamically typed, you can do whatever you want, you can make library calls. So there's different challenges, yeah. Yep.
Can you make network calls from Python UDF?
Yeah, so it depends. So I think the way that it works is that all these Redshift, Snowflake, Databricks, what have you, what they do is they provide some sort of restricted environment where you can't do any sort of side-affecting operations. You can't do I/O, you can't go to the network or do anything like that. And that's for security reasons, I believe. Yeah. Yeah.
Do you always do this optimization? If it's, you say RBAR, but if it's a 10-row table, how does this impact the query cost, or is
Yeah, so the question was this whole thing where you either inline or outline the UDF, that has to be done presumably before query optimization. So doesn't that take time? What happens if you spend all this time translating the UDF and then when you run the query there's like 5 rows or something like that? Yeah, so it's a great question. So the way that it works is that this inlining, outlining stuff is implemented in the binder part of the database system, which is essentially after you create function or after you write your SQL query, it does this sort of analysis or like optimization before it does query optimization, like looking up, oh, this column belongs to this table and things like that, right? So during binding, it replaces the UDF call with the translated SQL expression. And you're 100% right, which is that if you have a query that's super fast to run RBAR, then you're going to be wasting your time translating it when you could have just run it RBAR and it would complete. I think in practice, even SQL Server, at least from my experience playing around with it, it can actually detect that your query is going to be very short running and skips inlining. And that seems to be like a reasonable decision. Yep. Yep.
So for the P-SQL queries that you listed in the paper that weren't able to be optimized by PRISM, what are some of the problems that you saw?
Wait, let me. So I think the question was, in this part at the end with the experiments, here. Yeah, there are still 3 out of 15 queries that couldn't be optimized, that couldn't be unnested after you do PRISM, right? So I think the question was, what's going on with these 3 queries? Why couldn't these be optimized by SQL Server? And the answer is that SQL Server, although it does support subquery unnesting, you can think about it conceptually as pattern matching. It's going to pattern match and say, oh, your subquery looks like this. I'm going to rewrite it into a join. And then they have a bunch of patterns that they match against and then do the rewrite. But the problem is that if someone hasn't seen that pattern before, then they won't write it into the code of the database system. And then even if your subquery is really simple, if no one has written the pattern matching like subquery, like for that pattern of subqueries, then it doesn't get unnested, and it doesn't matter what you do, it's just not going to get unnested. So this is really like a problem with SQL Server, to be honest. Yeah.
Is there a possible method for generalizing that rather than going based off of previous patterns?
Yeah, exactly. So you can just use the German paper that I talked about. The question was, is there a way that you can unnest any subquery? And yeah, you implement this algorithm. So it turns out that that algorithm is very complicated, and basically you can't really implement it in a system like SQL Server, because SQL Server uses like this tree shape to represent query plans. But in order to do all this unnesting stuff, you need a DAG. So unless they want to rewrite their whole query optimizer, which I don't think is happening, it's probably not in the cards for them to unnest any subquery. Yeah.